So let's talk about RSA, which was the original public key crypto system and still the one most commonly used. This was a military secret held by the NSA for about 20 years, apparently, and then it was reinvented by mathematicians on the outside. And the trick here is, before this, the only cryptography that existed was private key. You had a secret key, and you somehow had to transmit that secret key to the other person so they can receive the message. And RSA allows you to negotiate a secret key over an untrusted network without exposing that key, which sounds like magic, and it more or less is. So first you have to have a public key, which is a large number that's the product of two primes, and an E where you just pick a small prime number. It's usually 65537. And this is the encryption number, and the private key has this D, which is the decryption number, which is very difficult to determine from the public number because you have to have the individual prime numbers. N is the product of P and Q, and the problem of factoring a composite number into its prime factors is a famously difficult problem that nobody has found a good way to solve in the general case yet, although Shor has designed a quantum computing algorithm which would solve it efficiently if you could have quantum computing hardware that was precise enough, which we do not yet have. So, you can do this easily in Python. You can start with very small numbers, which are of course not secure, but to let you see how it goes, you can pick P of Q and P of 7 and Q of 23, and so then you get N of 161, and you calculate phi of N, which is P minus 1 times Q minus 1, and those are actually the usable values on the ring. If you remember the modular arithmetic from before, there are certain numbers that do not have inverses on a ring, and a ring that is not prime, this is how many there are. These are the actual number of usable values you can use for encryption on the ring. And so you pick an E, a 5, or any other number, and then to compute the private key, you have to do the same thing we did way back in the binary games. You have to find the modular inverse of E, because you can't divide in modular arithmetic. So you have to find something which you can multiply by E and get 1. And there is an algorithm, Euler's algorithm, to efficiently find this by a series of successive approximations, but you can also find it by brute force. So here we have phi n is the modulus, 132, so that means the numbers go from 0 to 131, and the next number is 0 again. That's the ring we're on. So what you can do, if you want to find the inverse of 5, is you can just multiply, try numbers like 100, 130, this is the first thing, just to see the modular arithmetic. 131 mod phi is 131, but 132 mod phi is 0. So now, if you want to find a D that will cause decryption, and you're trying to reverse 20, all right. Here we are. You're guessing that the decryption key might be 20, 21, 22, or 23, and here's E. So you just multiply 20 times E, that's 100, and so it gets bigger, 105, 110, 115, 130, and then you miss one and go fast to 3. So you went all the way around the circle and you missed 1. So the only way to get a 1 is to try going around the circle again. So you double these numbers, and up around 50, you'll find a group. And here you have 118, 123, 128, 1. So there you find it. 53 is the inverse of 5. That's the mind-bending stuff of modular arithmetic. So if you encrypt using 5, you can decrypt using 53. And that will get you back to where you started. So that's how you do it. She wants to receive mail. This is the other fundamental problem with RSA. You have to generate a key pair, and when you're done, you can only receive messages. You cannot send messages securely with the technology only at one end. The receiver has to generate a key pair. This is the main difficulty in this system. And when Edward Snowden in America tried to betray the NSA and leak top secret information from the military, he wanted to send it to Glenn Greenwald, a journalist, but Glenn Greenwald was not technical, and he couldn't figure out how to generate a key pair. This system is so secure that it will hide data from the NSA, but only if you do it correctly. And Edward Snowden was recording like YouTube videos trying to explain to Glenn Greenwald how to make the key pair, and he couldn't figure it out, so he had to get a technology assistant, Laura Poitras, to help him. And this led to something that really upset the U.S. Administration, because now top secret information was being handled by a guy sent to someone who was not technical and not even trained to handle it, and then shared with other people to get technical assistance. So this top secret information is leaking and spreading and going all over the place and getting everyone very upset. But anyway, that's the problem. So Megan creates a key pair and she publishes it, and now anybody can send messages to her, which she can decrypt with the private key. But it's a one-way system. It only lets you receive. You can only send if the other person makes a pair too. So the only thing she tells the world is the public key, 161 and 5. But in private, she knows P and Q, and she knows D, so she can decrypt the messages. So you have to send a message. So you have to somehow convert this message to numbers. And the simplest way is just encrypt the letters one by one. That's what we're going to do here. So you have 72, 105, 33. Those are the ASCII values of this message. And to encrypt it, X is the plain text. You take the plain text to the E mod N. And E and N are the public key. So those are the two numbers. You take whatever number you want to send to the E mod N, and that will scramble it in a way that nobody can reverse it without knowing D. And nobody can find D without knowing P and Q, and nobody knows how to find P and Q from N. So that's the security. And anyway, there it goes. Anybody can send her messages, and she will decrypt it by taking the encrypted message Y to the D mod N. And you can see that works. That takes it back to the original. So there's a few challenges here where you send and receive messages. And that shows the fundamentals of how RSA works. There are a lot of problems with RSA, though. There are certain prime numbers that turn out to be poor choices with the wrong mathematical properties, and they're not obvious. And then there's the issue of quantum computing. Probably in 20 or 30 years, this system will be insecure even with very long keys. So it's really kind of got a limited lifespan now, but it is the original public key cryptography that we're all using all the time on the internet.